Now we're going to look into something a little bit more involved called acid nomenclature. You have probably heard of acids. That's a pretty big part of sort of what we use in daily life, but there's also going to need to sort of categorize them. And so acids, generally speaking, are a subcategory of covalent compounds. All right, so that, again, should spark a little bit of information. Make sure you're thinking, okay, this is going to have a bunch of nonmetals involved. In general, the formulas of acids, this is a great way to help identify things. The formulas will always start with an H, right? That's kind of how these always work. Now, you might see H's elsewhere, but generally speaking with H's, it has to generally start with the H at the front. When it comes to acid names, this one's just pretty obvious. It's going to have something acid in the name. It'll have the word acid in there. There are two subcategories then of acid nomenclature. So amongst all of the acids, there's one type called binary acid, and a second type called, let's try that again, acid, and a second type called oxy acid. The great part about these names is that they kind of give you sort of a clue as to what they're made of, right? So what they're composed of. Let's start with the first one, binary acids. First of all, binary acids, that word binary showing up again. So the word binary referring to acids that contain two elements, and one of them has to be what? Well, we just defined an acid as something that has a hydrogen in it, so the other one's going to be hydrogen. The name, right, so these are some clues to help you identify these more specifically as binary acids. The name will contain the word acid, I'm going to drop that in there, and it also contains this hydro prefix. Okay, so hydro, H-Y-D-R-O, kind of obvious as to why. The formula then, as always, we'll start with an H, and then we'll contain one other element, but more specifically, it will contain one other non-metal, right? Not just generically element. Now, that's again kind of a pretty characteristic description here. The key again is the fact that it has hydro as a prefix in the name. We'll talk about how that plays into our identification later. Now, let's go ahead and see some examples of how you go from a formula to a name. So like I said, the first word, trying to get the name here, right? So the name is going to have three parts. You're going to have that hydro prefix, right? So like I said a minute ago, you're going to have the root element involved. Again, this is that same non-metal that we mentioned earlier. And then finally, you're going to have an ic ending. So it's going to be hydro element ic. That's going to be the first word of the acid name, hydro element ic. And then the second word is just going to be acid. All right, let's go and see some examples here. All right. So in this process, let's go ahead and get it from a formula to a name. We have the formula HF, always identifying the type of acid or the type of substance. HF, I see that there's two elements involved. It's going to be binary something. And the fact that it has an H in front lets me know it's going to be a binary acid. So I'm going to off to the side here, jot in BA, right? Binary acid. And so since binary acid, there's a certain name, format when you write the name out. Let's go and figure it out. H, of course, is just the hydrogen part of it. F is the element root. So let's try this out. The first word has three parts. It's got hydro. And then the root element is going to be fluor, right? And then that last ending is going to be ic. Right? So we're not just going to write out hydrofluorine, ic. It's going to be hydrofluoric. And then, of course, because it's an acid, we write the second word, acid. So hydrofluoric, all one word, acid. HBr again, similarly, we're going to take a look at the type of compound it is. It's got an H in front, so we know it's an acid. There's only two elements involved, so it's going to be binary. So in this case, it's going to be a binary acid. So write a little BA next to it to remind ourselves of that. Let's go and do the name. So Br is that root element, the core element here. So we go ahead and use hydrobromic, and then acid, right? So hydro element root ic acid, hydrobromic acid. Let's go the other way. So now we're going to talk about the formula. So the formula is going to be pretty straightforward. In this case, the first element is going to be H, like we said a couple of times now. The second element symbol is just going to be whatever root element's in the name. All right, so let's try this out. First of all, looking at these examples, hydrochloric acid. All right, so how do I know what kind of substance it is? Well, it's got the word acid in it, so that's a big clue. But then we know it's going to be a binary acid because it has hydro as a prefix. Now, again, like I said, that's going to be an important key here. So I'll remind you about that to know that this is going to be a binary acid. All right. And then let's go ahead and write the formula. So it's going to be H to start, always and forever. And then the core element was chloric. So we knew the element was chlorine. That goes into the formula. Hydroiodic, same process. you see a hydro, something acid. Acid tells you it's an acid, that word. It's going to be a hydro prefix, so we know there's going to be a binary acid. Then, because we know the first element is going to be H, there's always going to be just one other element for a binary acid. It's going to be iodine, so just high. All right, that's binary acids. Let's see how oxyacids work. Now, oxyacids are a little bit more involved. And once again, there's going to be some comparison between oxy and binary. But first, let's go ahead and define some of the particulars. First of all, acids, of course, that contain oxygen. Right? That kind of helps because oxyacids contain oxygen. Now, this is, again, one of those things where it actually, again, has a lot of sort of varieties that don't have oxygen, but broadly speaking, yeah, it's going to have oxygen in it. We'll see some examples later on. These will have at least 3 elements. Okay, so the name. Let's see how we can identify these by the name. So the name will contain that word acid, right? Pretty straightforward there, but it will not contain the hydro prefix. Right? So I've already kind of highlighted this a couple of times, so I'll do it again. It will not have the hydro. Right? Well, maybe I should do that not part. So the hydro is a pretty nice telltale sign of it being a binary, not an oxy. On the formula side, it'll have an H, and it'll have a polyatomic ion. Okay, so in case you're wondering, these polyatomic ions, right, those aren't just for ionic compounds. They actually have applications here in oxyacids too. By the way, the formula, this language right here, to have an H, meaning it'll have some H's, it might have more than one. That's in comparison, of course, to the previous one where all of them just had one H. This time, it might have more. So just keep that in mind. Let's do some practice. Switch it from formula to a name. If we look at the system right here, focusing on how to write the name out, the first word, what we're going to do is we're going to take whatever polyatomic ion is in there, right? So the key here is identifying the polyatomic ion. We're going to do some stuff to it. We're going to modify it by looking at the ending. So if the ion ends in an 8, we actually switch it to an ic. So 8 gets switched to an ic when you go from the polyatomic ion to the acid name. If the ion ends in ite, ite, we use the OUS ending, us. So ite becomes us. 8, ic, ite, us. That's the first word. So we take the polyatomic ion, switch the ending in the first word. And then the second word is just acid. All right, here we go. Let's take a look at some examples. First one, HNO3. HNO3, of course, we're looking at the type of compound before we do any kind of naming. You see H in front, that's classic acid, but more specifically, which kind of an acid? It's going to be an oxyacid, or oxyacid. How do you know it's an oxyacid? For 2 reasons. One, again, you see the O there, but more importantly, you do recognize that NO3 is the formula for one of our classic polyatomic ions. So at this time, we have an H, a polyatomic ion. That's going to be an oxyacid, so I'm going to draw a little OA next to it. So let's go and follow the process for oxyacid work. First of all, the polyatomic ion, like we said, is nitrate, right? So nitrate is going to help us here because we're going to take the ending ATE, check up here. We're going to switch that then to nitric, right? So that becomes nitric. And then the second word is acid. There we go. Over here, H2SO4. All right, so let's go and break this one down. H2SO4, if you notice, right? H in front, you got SO4. So we have an acid. It's got the polyatomic ion sulfate. And so once again, we can tell that this is going to be an oxyacid. Sulfate, right? Sulfate, okay? This one has an ATE ending. And we're going to switch it to an ic ending. But of course, this is one of those weird exceptions. But, I think you kind of have heard of this before. Instead of just taking it straight to sulfic, this one actually then gets translated into sulfuric. So this is a strange one. Again, this is one of the only 2. I think the other one might be just your phosphates, which we'll see later on. But the idea here again is sulfuric and then acid. All right, so there's a funky one that doesn't get straight from the 8 to the ic. You actually have to do a little sulfuric acid to it. Also notice that we didn't even consider the fact that there's multiple H's, right? There's no need to include any prefixes. There's no need to have like 2 H's in front, right? That's not really necessary. Recognize, what have we left off entirely? There is no hydro prefix, none of that. Now up here, you might be wondering why these 2 pictures are here. Well, again, this is going to be a tick, right? And then this is going to be a little bit of redness here. So that's usually the ending. When we talk about medical conditions, a lot of times you have a redness and swelling. That is a suffix of itis. So again, what exactly does this mean? Well, if I take 8 ic and say it fast enough, right? 8 ic sounds kind of like a tick, right? A tick, 8 ic, a tick. So this is a tick. And then if a tick bites you, right, you get a little bit of redness and inflammation, so that's become itis. So this itis. So a tick, itis. A tick bites you, and you get a little bit of inflammation. We have the suffix itis, a tick, itis. All right, let's go the other way. So now we have it from the name to the formula. This one's going to be a little bit more involved, but still, again, follows the same principles. First of all, you need to identify the fact that you have a polyatomic ion in there. And in this case, writing the formula out, right, you're going to actually have to add enough H's to balance that negative charge of the polyatomic ion. So in case you haven't noticed, right, most of your polyatomic ions are negative, and so there's going to be a certain number of H's that get added on there. More importantly, though, not just the H, right? H's, if you kind of think about it as a charge here, right, H would have a +1 charge because it is in group 1. Now, I know H's are not metals. We don't really expect to do that, but in this case, we treated it like that. So although these are all covalently bonded, there's some amount of it that you do have to kind of do a little ionic compound treatment in this situation. All right, let's try these out. So let's go and see, we have the word acetic acid, right? So the word acid right there is a big clue. We know it's going to be acid of some kind. What kind of an acid though? Well, what do we notice is not there is that we don't have that hydro prefix in front, right? So none of that hydro in there. So it's just straight up acetic acid. And because there's no hydro prefix, we know this is going to be an oxyacid, right? Now, with that said, right, we have the word acetic acid, right? We have to identify the polyatomic ion that it came from. If it ends in tic, right, IC or ic anyway, we know that it would come from a polyatomic ion that was acetate, right? And we have an acetate polyatomic ion, so that's going to be C2H3O2. And of course, acetate, right, if you look at the list, acetate has a charge of a -1. And that means we have to add a certain number of H's to it in the front so that we can balance out the charge. And it turns out you only need one of them, right? Because H is also +1, acetate's a -1, so only one of each, and we're good for a formula. That's your formula for acetic acid. What about phosphoric acid? Okay, so let's try this one out. Phosphoric acid. So in this case, right, one more time, acid is in the name. We don't have the hydro prefix, there's nothing there. So this is going to be an acid, but more specifically, oxy acid, no hydro prefix. So with that said, the polyatomic ion, phosphoric acid. Phosphoric acid is actually then going to come from the polyatomic ion, phosphate, right? Again, once more, this kind of strange sort of dropping the ic and becoming or, you know, it's basically one of those things, kind of like the sulfate, sulfuric things. It kind of changes a little bit. So we can't call it just phosphic acid. Whatever the case, we're looking for the polyatomic phosphate. Phosphate has a formula of PO4 with a -3 charge, right? But of course, we're writing a compound, and those don't include the charges. So we have to add basically enough H's, where if individually phosphates are -3, H's are +1s. To balance it out, we throw 3 of the positive ions to one of the negative ions to make H3PO4 as your phosphoric acid. All right, that'll do it.